Yeah, the feedbacks need to be understood because if you look at the predictions of climate model in the next 100 years, depending on what scenario you use, which scenario you are going to go to, you get numbers, you get a range of numbers, not one. Each of the scenarios is a range of numbers. And the question is to understand why different climate models for the same scenario they give a range of numbers. And that's because the feedbacks in different models is different. So that is the main problem. Here's another example. This is about 12 models that are compared for dumping of CO2, and they give 12 different answers. Okay? And the answers vary from 1.7 degrees to 4.5 degrees. It's a huge range. Okay? And this has caused a lot of problem for IPCC because people are skeptics say there's so much variation, we don't trust your models. So a lot of effort has been put in to understand why these models show such a large range. What is the difference in these models? These are all have the same change in the outside, but why should they vary by a factor of 3? Okay? And the attempt in the last 20 years has been tried to narrow down the model differences so that there is some clarity in what is the most probable thing. But in spite of the criticism people made, I want to look at it differently. Forget about these extreme cases here. And most of the models are green. 3.5 most here. Over 10 models 3.5, if you are bad here, if you are bad there. But I would say what we should be doing is to examine these models to understand why it is so low, why it is so high. That's what is important. Most of the models are showing around 3.5. This is repeat, I don't know if we need this. I don't know why it is there. Yeah. This is already covered in the morning, but this is a point which I just want to discuss about this since it's come here, showing the typical value of solar constant varies between 365.5 to 366.5. That is the kind of oscillation. And interestingly, the latest one, which is now, so that here is pretty low. So there's one mystery about why this particular solar minima is lower than the previous two. So a lot of debate going on among solar physicists to understand what controls the minima. So there is a possibility, interestingly, that in the next 5 years, the present solar minima may be one of the lowest in the last 100 years. In which case, global warming not be seen for another 5 to 10 years. So that's a possibility that this is one of the lowest minima, but still, it's in the range not much. This is 2 watts per square, this is 1 watt per square, this is around, this is 1, this is 0.5. Okay? So you're talking about at the most 1 watt per meter square, 1366. So it's around 0.1% even less. That's the, so it can only explain about 0.1 degree change in temperature, not more than that. Now, when Milankovitch looked at his hypothesis, he argued that in the summer, during the last integration of the very warm, the summer polar region had 50 watts per square more radiation coming in than normal. And he claimed this is what caused the additional snowmelt and caused radiation, that is a warm period. The trouble when he did this work was that this additional 50 watts was not always there. We average over the summer season, April to September, for example, no more like 35, and that's how after that actually it was less. So in the short summer period, snow has to melt. That's all the time it happens. Otherwise, in the winter, actually the radiation is much less. So his calculation got into trouble only because although there is a large additional solar radiation in summer in the period time, they are not long enough. And what is remember is the challenge in the space was during the ice age, the typical thickness of ice in the polar region was 4 kilometers. Okay. Now here to convince his fellow scientists that because of the 30 to 35 watts additional for a 4-month period, the entire 4 kilometer ice will melt. Okay? That's not easy. Now all of you, this is high school calculation. You know what the latent heat of melting of ice is. you know the thickness of ice, you know the mass of ice, you can calculate how much energy is required to melt, a lot of energy is required. So, if you base it on this calculation and a reasonable absorptivity of snow, you will get a number something like, I think maybe more than 100,000 years. So, it isn't trouble. So, the only reason later on this model is acceptable is because of the feedback which is complete. That feedback, when ice becomes water, it can absorb more, and CO2 increases, methane, all that, electrons will not happen. He just based only on additional energy coming in, and that didn't help you because the amount of energy required to melt ice is very large. Okay, now today we have done a very nice piece of work because we have now this big model which you can run. So models are run for last ice age and the present climate, and this result shows how much warmer today's climate is compared to the last ice age 80,000 years ago, and what are the contribution of different parts of the system. So that is what is required to understand the full climate system. So according to this model, this is a model, so there could be some model dependent results. But by and large, what we are saying is orbital variation only contributes this much. Look at this number, very small, around half a degree or maybe, sorry, this is half, this 0.1 degree is in effect of orbital variation. Everything else is feedback. For example, what we expect is much larger today than last I said. Clouds are different, so they contribute to 2.4 ppm. So from the last age to today, most of the warming is water vapor, not this as a trigger. The next one is land ice. Land ice is disappeared completely, almost. So that contributes to 1 degree, 0.9 degree. Sea ice disappeared a lot in the last 80,000 years. But so this is 1.6, and it says much is comparable to water vapor, and the vegetation change a little bit. CO2 is higher now, 100 ppm, that contributes around 0.6 degrees. So the point is that it is useful to run these models and ask what are contributing each of these parameters, and then you get overall data. 2.2, 3.1, 3.8, 4.1, 4.75 degrees. That is the typical number for people between last ice age and present 5 degree changes occur. But remember, it is not due to this alone. This is very small. Okay. So that's why remember we said from my example, because that's all right. You can explain 1.2 degrees, but you can't explain 5 degrees. So all these feedbacks are necessary. And dominant one is water vapor, second dominant is ice, third is CO2, the last is methane. Okay, one more. Okay, the other model is the other answers. So this result that we got, this already I talked about. Yeah, so let me point out another problem that occurred in feedback discussions. So this is simple argument that we give that you change CO2, that is external trigger, forcing. And that causes changes in water vapor and all, so that's the feedback. In this case, it's very simple. We know that the CO2 increase occurred in the last 100 years due to human beings, and we treat it as external because we are the ones who do it, and that's a force. But I must tell you that it's not that simple. What is forcing and what is feedback is not that simple. I'll give an example. Take methane. Methane is a gas which causes not a greenhouse effect, but a powerful one. So imagine an event, a lot of methane was emitted to volcanoes. That will be a force. Because volcanoes are also external to the climate system. Suddenly it came out, put a lot of methane, that caused warming and that caused something else. But today, when we are putting out CO2, due to human-induced changes, methane can come out from some source. What source? The most common source of methane today is going to come out in the next 100 years. It's called permafrost. This is frozen soil. Okay? And lots of Asia, especially Tibet and beyond, Russia and so on, contain large portions of the land which is frozen below the surface, or at least around 10-20 meters or even more. Now, what is frozen in the soil contain? Methane. Methane is trapped there. So, as we increase CO2 in the atmosphere, and the atmosphere starts warming, that frozen soil starts getting melted, unfrozen, and methane comes out. So people have measured methane coming out of various places in Russia. So in this case, methane comes here as a feedback. Okay? So methane can be a forcing or feedback depending on the situation. So you might ask, since methane can be both forcing and feedback, how do you know in a given situation which is for the feedback? So the answer is rather simple. If it is feedback, it must depend on temperature. Temperature will trigger the change. Like what way the feedback? Why? Temperature change very happen. So methane is increasing the atmosphere due to temperature change, it's a feedback. If methane is due to volcanic eruption, that's not temperature, that is not the earth science phenomena, plate tectonics, which is not temperature dependent, then that's a different story. So one has to understand what triggered the change. It is due to temperature change or due to some other change. That is what I understand. And interestingly, I give an example of the 20th century CO2 increase, which increases temperature and methane goes up. But the very interesting hypothesis by famous climate called Rudiman. Rudiman argued, see, RPCC has always treated 80% as a border. Because this revolution possibly also birth. He said, no, that is not the border for anthropogenic change. Actually, the real change occurred 5,000 years ago. 5,000 years ago, agriculture became very common in Asia and Africa. They did large-scale deforestation and planted rice mostly. And when you plant rice, you generate methane. All of you know that rice grows in mostly marshy lands. So he argued, based on actual data, that the methane increase between 5,000 years ago and now cannot be natural. It is due to this. However, we don't agree with the big debate going on because our data on methane between 5,000 years ago and now is not very accurate. It is based on ice core data, and you need to do a lot of careful analysis to. But he is convinced that human being not there, the methane would have gone down, and not the way it's going down. But so in that case, methane is an external force because human beings, by converting forests to agricultural land and putting rice there, they introduce methane into the system. That is not temperature dependent, that is human use. So you must remember that what is feedback is not at all simple, but the main distinction is feedback depends on temperature, forcing is a factor which is not dependent on the climate system, but external climate system, human beings or volcanoes or some other cause, the sun, for example.
Similarly, soil codes can be taken out, like similar to ice codes.
Yes, you can, but the top layer soil is entirely atmosphere. You have to go deep with that. Yeah. For example, Sukumar has done it. Sukumar in CS, he has gone to OT and taken a long course and he'll tell you what was the climate of OT 10,000 years ago. You can see, based on carbon, yeah, you can do it. But you must, top 1 or 2 meters are not good. So this is a definition. Supposing has an external perturbation, solar organ, human being, something which changes without being influenced by the system. That is the key. And the feedback is response to system change, which is due to temperature. Okay, so this is the normal schematic illustration of the feedback. This is there's no feedback. There is so much of consumption, so much of temperature. Now we talk about feedbacks, how the feedback occurs. Suppose you change the forcing by some watt meter square. Like for example, if you increase CO2, you double CO2, additional traveling is 4 watts meter square. And that will cause about 1.1 degree change. But without feedback. Feedback I wanted to come into this diagram. Now let's put the feedback. Now just to show you, many years ago there was an experiment run with the climate model in which they wanted to show the effect of doubling CO2 with and without water vapor change. So the control run allowed water vapor to increase as per normal thermodynamic laws. The other one deliberately fixed water vapor. So if we fix water vapor, don't allow it to change, no feedback, then the warming is around only 1 degree. exactly what we said in the previous slide. Okay? But this is the no feedback case, the bottom one. Okay, and yeah, so this, no, sorry, this one. So this is no feedback case. Now the top one is with all changes, clouds, water record, everything, it goes to 3D. So this difference between with feedback and without feedback is what we have to analyze carefully, understand what are the things which contribute to the increase 1.1 or 3. So that's the purpose of the feedback analysis. This is the picture you get. You take a Sherman bottle, you get a forward municipal increase trapping due to CO2, and you get 3 degrees. And you ask why it's so, you see that what we have contributes additional 5 watts trapping, less known ice for the 1 watt municipal trapping. In this case, decrease in cloudiness causes 1.5 municipal trapping. And what if the probability is changing? That also causes some change. This minus is not plus, but it is causes cooling. All of them you add up, you get the 3 degree change. So that is the logic. Logic is that initially there's a forcing, then the CO2 changes, sorry, whatever changes, land changes, we all cause additional forcing. All that add up to the result for 5 or 6 watts per square additional beyond 4. You can also have negative feedback. We'll see what it is like. Now, this is a better way to explain that. It is in the context of tutorial is very important. So we start with the current climate, which from which we got an answer. You get this from here, you get this from here, and make a round number 240 over top, 240 over here. Simple. Now I double the CO2. The 240 becomes 236 going out. Incoming can't change right now. Immediately can't change. There is no free practice. So what happens is the earth temperature has to go up 1.2 degree in order to balance that 4 watts. Okay. So I gave you 2 watts here, this 4 watts will be double. So this additional thing is forced on you because this is not changing. If this is not changing, only way it can put out 240 as before with additional CO2, still 140. Now, with feedbacks, it goes to 3. But still balance is the same, balance not change. I hope all of you understand. Ultimately, absorbed solar, in this case, is fixed. It can also change. Your absorbed solar is fixed, and there are more and more feedback with water vapor and ice and so on. That's why just go further and further in order to get to the same heat as before. Is that clear to you? So ultimately, the earth has to put out certain amount of heat equivalent to what it absorbs in the sun. Okay? And of course, this simple model, you're going to make more complicated. One more round, I can say, because things like this also change, that can happen. Why it would happen? Because clouds are there, and clouds change, the albedo will change. So the 240 also will change. So this can be simple. It's very simple. From a course, so here is assume that visible region changes are not there and it's infrared. So this is mostly water vapor and other factors is changing this one. We have kept this constant, but really even that can be changed in both directions. It can increase the decrease. Yeah, so the notation for feedback is standard control theory notation. This is your system, this is your input, this is your output, and your feedback that modifies the input. So that is the way we think about it. And this I'll explain a bit better. This is a little bit not clear. K0 is the so-called gainless system from input output. Without feedback sound, that's a gain. But all these changes in albedo, water vapor, laminated particular temperature profile, cloud cover, all these are dependent on temperature change. Okay? All these are internal feedback. So I'll graph the graph. Let me see whether I have actual derivation. Oh. Let me see. Yeah, this is the one I want to use. So initially, there is temperature change, okay, without feedback. That's initial CO2 increase. Then CO2 changes, then other temperature changes occur. But finally, this is it. Okay? Now, historically, the feedback is defined as the additional change by the total change. Now, I warn you that definitely will be non-standard, unfortunately, but that's what it historically is, I cannot change it. So, I would prefer this by this. That is really logical. But for whatever reason, because of the background of control theory, so we prefer to use the final data T as the criteria. That's the feedback. Okay? So, if you put that definition here, it comes on this side, so you get this value. For one feedback. There are many feedbacks in what sigma. Now remember, this formula is partly related to definition value, not very, but it has an important issue. So this is the original condition change, but 1 degree, 1 degree, and this is the amplification due to feedbacks. Okay? If it is 0, there are no feedbacks. If this is positive, this number will go down, this will go up. If it is negative, the number will increase, it will go down. So that is the positive negative feedback definition in control theory. Now when I give this talk to people who are managers, I talk to many managers in corporate talk. When I say positive feedback, they think is good. But positive is not good, it's bad. But anyway, it's not positive because of this definition. Positive here increases this, not good for us. But many of the managers thought positive feedback is very good, why are you against it? But remember, this is just a way to define. The positive feedback is accelerates the amplification, not good for you. You want negative feedback, but they're not doing negative feedback the system. Yeah, so this is already defined here. Yeah, now this is caused a very interesting consequence which is looked at. The gain, which is the final change by the initial change, that is the gain of the amplifier there, depends non-linear on F. So it's in the graph. So this shows that system can go unstable very often. So as F approaches 1, the competition gain you get is huge. Okay? So this is the thing which concerns many people about climate change. That there are many feedbacks, which include those we know and those we don't know. See, the other point we have been facing is research going on for the past 30, 40 years. Every 5-10 years, people come with new feedback going on in the system. For example, this permafrost was not known about 20 years back. Now, people measuring methane in Arctic and Russia, they find methane coming to the soil. That's a new feedback, we're not that early. So, we won't add numbers to this sigma Fi, which when they started have only 1 or 2. This thing is increasing. This number of possible feedbacks. So if it approaches 1, we're in trouble. If it approaches 1, then the system is what do we call runaway. This is what we call runaway. Runaway means after some time, even if you stop increasing CO2, the system will keep increasing. Okay? That's what happened in Venus. That's a Venus is such a famous example that with no external motivation, with no trees or nobody was there, it went on in one direction. So something happened and then it took off. So that is so the point is, this number even approaches 0.9, we're in trouble. 0.9 with 0.1 will amplify in 10 times. The CO2 causes a 1 degree change, due to feedbacks, it can go to 10 degrees. So that is the issue in a debate where everyone, are we able, do we know all the feedbacks? And do we know exact quantity what the number is? Because if this is 0.1, I don't worry about it. If it's 0.9, it's a cause of worry. And that's why this graph is so illustrative of this runaway feature of this feedback. If you're somewhere here, no problem. 0.1, 0.2, 0.2, no problem. Somewhere you go past the near the curve of 0.6, it takes off on its own pretty much. Now, so this uncertainty and this again shows the answer, but the point I want to make is that today our knowledge of feedback is not perfect. Right? There is still a lot of debate about what is feedback. So feedback does not have one value. It has a range of values, a distribution. So if this has distribution, let's say the most probable value is around 0.7, and it can be 0.4 or it can be 0.9, this distribution. You multiply that with that, then the distribution of possible temperatures is skewed. Now, I want you to remember this because you remember in the morning I showed you on the graph. And I asked this question, delta frequency with delta T. So like this, you remember? All you remember that? You can explain that from these. Why it is like this? On the low temperature change end, it is very sharply. There is a long day, very high temperature change. This is coming from here, this is high temperature change. This is low temperature change. So this skewness is due to the fact that we don't know the F value precisely due to model problems. And this is related to the 1 by 1 example. So I want you to appeal the fact that you should expect the temperature response not to be symmetric. I want to remember point here very important. Notice that this is symmetric response. I assume that my uncertainty about F is symmetric about some value, 0.7. So I don't know anything about it, I'm assuming it's symmetric. I got it, for example. But the response is not Gaussian. Response is skewed. And that's because of the way feedback works in the system. Okay? So this is an output from model we saw, it exactly has this shape. Even more students will more like this. So that shows that even though the input uncertainty in feedback is symmetric, the output of the model will be asymmetric in the response. There is more probability of much higher temperature change than low temperature change. And that is again cause of concern. These are some numbers which I don't want to bother about. Yeah. Now here I am giving you various feedback parameters from actual models to show you the kind of range and possibility we have. Water vapor is one of the simplest feedbacks you can think of. Unfortunately, in the model there is a range of values. These are different models for 12, 15, 21. Then clouds, even the range. Albedo, that is mainly due to ice melting models. So some range might not happen. Then max rate, because the vertical temperature profile changes and they change into different models, that has a range. But what people did was finally they combined these two very connected, or the temperature profile change model also change these two connected and we get a combined feedback. But the main point of this analysis is you add all the feedback, you get this final range of values. It is mainly related to this one. That's clouds. So among the feedback parameters we have in climate models, the most uncertainty is caused by one thing, which is clouds. Water vapor and lab state translates out a little bit, and albedo range is not that much, there is something but not that much. But this guy is a huge range. And so that's why all the focus of our work is related to cloud. The cloud is one which models differ so much among each other. Okay? Now I want to give a different view now. So we have a very simple view about polar, linear temperature, and so on. That's okay if the temperature range is small. Suppose you talk about finding the linear change, then you can linearize the equation and do it. But what happened in Venus is more interesting. Venus had a much increase in temperature. Venus was like Earth at 288 or even probably lower. It went up to 700. So when you go to such a large temperature range, then your linear model is not valid. Okay? So what happens if you plot OR in Venus in temperature? If there is no water, the RS is no water vapor, then you get this conventional smart for that. But if it's saturated, which can happen, there's a lot of ocean there, it becomes like this. Okay? Now, why is it so critical? How we measure this? It says beyond certain temperature, polar cannot change. Can anybody see why? Temperature of the plant is increasing, but overall is not on the increase. Why is that? It goes against our thinking here. We are saying PS goes up, polar goes up. That's only valid for a narrow temperature range of 10 degrees so. When it's got 140 degrees, polar can be invariant of temperature. Why is that? Huh? No, albedo is unchangeable. Albedo is fixed.
Everything is only
Yeah, the whole point is that if RH is fixed at unity, as the temperature goes up, according to the Clausius-Wilbur equation, the water temperature of that atmosphere will go up exponentially. The water goes on increasing, so it drops more and more radiation, and the Earth will not get rid of the heat. So what it's saying is that there is an upper limit of how much radiation you can emit. In this case, this is only example 300 watts per square. Okay? So this is because, remember, this is only the emitting radiation. Remember that in this balance, these two are independent almost. This balance when you do, this is independent. This is the visible region, in fact, this is the region of long wave. They are not necessarily connected. So if you say this is not easy 300, and if you are unlucky, and if you are on a planet whose albedo is low, let's say 0.1, okay, then it's possible that this number may be greater than this number. Right? Then there is no balance possible. The planet will run away because then somebody asked me about this steady state model, then do a transient model, that's what happens. So the transient model will say that heat capacity plant is C. This is a model for transient. Okay? Now here you see the interesting phenomena that if somehow this number is always greater than this number, and this number is fixed at 300 according to that model, then this temperature will never be steady state. So what happened in Venus? This is what happened in Venus in the earlier part. It had an ocean like Earth. As temperature went up, all the water evaporated into the atmosphere. Temperature went on increasing 100, 200, 500, 600. Then, as all of you know from chemistry, water dissociates. Becomes H2O2. Then H2 escapes. H2 is greenland gas, it escapes. Very soon there is no water vapor in the atmosphere. Then what happened? Then something more complicated happened in Venus. Temperature became so high that all the rocks started breaking. All the carbon dioxide rocks came out. That's how it was like Earth, with all the carbon dioxide trapped in the ocean and in the rocks. When the temperature goes up so high, then the rocks become reactive. So all the oxygen carbon dioxide comes out. So finally carbon dioxide in Venus is about 1 million times larger than Earth, million times. Okay? Yeah.
So could it be so that since there is no plate tectonics also on Venus, since there is no plate tectonics on Venus, the CO2 could not get recycled?
Yes, but the phase change issue is not there. The more important issue is that you need water for CO2 to dissolve. Okay? Phase change is one issue, you're right. See, remember CO2's freezing point is very low. How do we know what do you call that? Solid CO2. You have to go to very low temperature. That will not happen. It will happen in maybe Pluto or something. But in all the planets close to the sun, the such CO2 don't exist. So the beauty of Earth is that CO2 was dissolved in the ocean. That was the key. You need water. Liquid water has to be there, so dissolve. Once liquid water runs out, they're gone. They're out of business. So it can happen on Earth also. If all the water evaporates out, then there's no choice for CO2 to anywhere. Even today, I tell you, of the 8 gigatons of carbon we're putting into the atmosphere, about 50%, 25% goes out today, but goes into land. So suppose the ocean cannot dissolve the CO2, so it will keep building up in the atmosphere. So, but this temperature went up so large that chemical reaction took place, which brought out CO2 out from the silicate rocks that came out. This, I think this is covered. Yeah, the other important thing we must understand why models are doing badly. We saw that CO2 dumping caused overwatts of respect happening. Okay? But a typical change in the flux tube, the reflection rate of 48 watts per square, and a reduction in radiation per charge of 31 watts per square, net effect is 70 watts per square, sort of. Okay? Now, this is much more than 4 watts per square, much more. So what this says is that in Earth's atmosphere, 1% change in clouds will have as much impact as CO2. And the problem here today in both observation and in modeling is that we do not know the cloud flash of the Earth but accuracy one below. We have satellite data for around 50 years, but nobody can claim we know that the cloud content is this value. This is the other problem. Okay. So this is the point to remember that the impact of clouds on the radiation belt of the Earth is much stronger than impact of CO2. And that's why there's a huge error bar in the future, because we are not clear about how clouds will change, whether they will increase or decrease, and we are not sure which kind of cloud. For example, clouds from a variety of hope is there in this presentation. Yeah, let me just quickly. Okay, take the satellite data. It shows that albedo of the average Earth is 30%. But if you look at cloud-free Earth, it's only 15%. Okay, so half the albedo is attributable to the cloudy region, and the cloud-free region, mostly oceans, is around 15%. And if you look at the how much solar radiation is absorbed in the cloud-free region is 288. The cloud-free region absorbs more CO2, more solar radiation because there are no clouds there, so more cloud is there. When there is cloud, it goes down. In the case of overlap, in cloud-free region, more radiation goes out to space. If there is a cloud, Earth is unable to get rid of heat because cloud cannot emit at high temperature because the cloud is very cold quickly. So this is the problem with clouds, and it is much more in terms of Watts per meter squared stronger than this. So these are various kinds of clouds. Our problem is when CO2 goes up, we don't know which of the clouds will change at around. These clouds actually warm the Earth because they are high clouds. These clouds, the lower ones, cool the Earth. Okay. So there are models in which you can solve and there are models in which this cloud increases, so the planet cools, so the global warming not much. There are models in which this cloud increases and traps more higher radiation and warms that. So all possibilities are there possibly because various cloud types react differently to the temperature change, and we do not have sufficient data to predict which clouds will change in which direction. Okay? So these clouds are defined in terms of how thick the clouds are, in terms of radiation absorbed, and what height the clouds are. So there are middle clouds, low clouds, and high clouds. And I'm only giving 9 types just to keep it simple. And so no two models agree on how much of each cloud can be changed in the small global. No model agree on it, impossible. So that is the major uncertainty about climate models. This you already covered. Yeah, this is an example to tell you how bad the situation is in terms of cloud fraction. This is based on 30-40 years satellite data. One satellite says cloud is increasing. Other satellite says cloud is not changing. Okay? We don't know. And notice that this is not change, not minor. There is 6% change in cloud increase. If this is true, then you need not blame CO2. Just global warming cloud reduced over the last 30 years. But there are big question marks about this satellite series. This is based on geodetic satellites around the equator of the Earth. And one of the sad part is, this series does not cover India. Because Indian government in its own wisdom didn't share the data with the world. ISAT data is not given to the world for what is happening now. It's kept like a secret. And so they have to manage without ISAT. So I think there's a serious problem with that. Otherwise, it's different. They're different than satellite that is polar orbiting. I trust that more than I trust this. But the polar orbiting satellites are not like it. Why is that? Because the typical cloud has a lifetime of 1 hour. Typical cloud. Okay? So in order to get correct picture of cloud on Earth, you must sample cloud at least once an hour. Now, unfortunately, polar orbiting satellites visit any point twice a day, every 12 hours. You cannot cover all the clouds. Geostationary satellites are much better. They are always the same spot. They are looking at the clouds every 15 minutes. But there are two projects satellites. One is that data for the entire globe is not given. Now it's given. Now it's been given by Indian government. Secondly, it doesn't cover polar regions. This is only, as you can see, because they just have only, like the garden around the equator, they can't cover it. So we have to combine these two, the polar and this combination answer. But as of now, there is no reliable data to tell us whether the cloud fraction is increasing or decreasing. Until we get that number, we cannot do anything about clouds. Now, you must remember that clouds also change naturally. Forget about climate change. This again is the data showing a gradual increase in high clouds over the last 20 decades, and that's about 3%. And not only the cloud fraction change, the cloud top height also changes. Now I want to notice the kind of change is going on, which is due to natural variation, not different. Look at this huge change we saw in 1991. Okay? And this is most probably related to an El Nino that occurred at that time in the Pacific Ocean, which increased the cloudiness dramatically. The cloud temperature changed a huge quantity. There's also, of course, the volcano which erupted, that also played a role. That's somewhere here. So you can see that even with no human intervention, large changes in cloud heights can occur on the Earth due to natural oscillations of the Earth system. I think this I'll leave. Yeah, this just to give you what is the contribution of the present. Presently, we have 0.3 as the planetary albedo. It is contributed because cloud fraction on 0.6 and cloudy sky as albedo on 0.4. That is 0.6, 0.4, 0.24, and the remaining 0.4 and 0.5. So that's the contribution. There is, in this case, 0.24 comes from cloudy sky and 0.06 comes from clear sky. So that is the number from one of the satellite data. Now the other important thing to remember is that cloud always change the amount of liquid water in the path, how much liquid water is there in the cloud. And notice that its impact on albedo, that is the reflectivity, the solar region, and this is very different. Notice that when the cloud thickness is around 100, albedo goes to around 0.5, 0.6, usually goes to 1. So cloud becomes a black body very quickly because liquid water is a strong absorber of infrared radiation and emitter. So the emissivity goes to 1 in the infrared very rapidly within short time. But albedo is still increasing. Because in the visible region, cloud does reflect, but not perfectly. So it requires a very, very thick cloud to get albedo 1. It varies somewhere here, but that's very there. Most of the clouds are here. So this difference in the response of the cloud in the solar region and the IR region has a huge impact on the way it changes Earth's climate. And the other complication is that not only that, you are worried about the droplet radius. The same one liquid or block, the droplet radius is different. The smaller drops reflect more than the larger drops. Smaller drops is here, larger drops is here. So that is another issue which is complicating matter. For example, as I pointed out in the morning, as we put out more CO2 in the atmosphere, we also put out more sulfur dioxide. So they affect the droplet radius. If there is more aerosol in the atmosphere, you get more small drops, so you are going towards that. So that has also played a role. The effect of aerosol on cloud reflectivity has also played a role. We don't know what the role is actually. I also skip. Yeah, this is a simple cartoon explaining the different role of low cloud and high clouds to Earth's radiation project. Low clouds causes more reflection. It doesn't cause much greenhouse effect because low clouds have the same temperature at the surface, so they don't reduce the amount of heat going out of the Earth. So low clouds will do the opposite. But if you come to high clouds, like cirrus clouds, the reflectivity is not very high, and they can mostly small ice particles. But because they are so tall, they emit a low temperature, so the heat is very large. Okay? So they warm up. Okay? If you take a very deep cloud of the kind you get during monsoon, the two effects cancel out and nothing. But mostly you have to worry about these two. If as the earth forms, more low clouds form, then earth will cool. As the earth forms, if more cirrus clouds form, it will warm. And unfortunately, as I told you earlier and I repeat it, different models give different results. Some models increase low clouds, some models increase high clouds, some models increase cloud factor, decrease all this possibilities are there. For example, if you have a model in which low cloud increases, it will cool. The same model, if low cloud decreases, it will warm. So both possibilities are there with low clouds, similarly high clouds. So this is the point on which there is no agreement in the observation or in the modeling, and that's why we are not sure about what clouds will do. Yeah, this is another way of explaining that low clouds are extremely radiation much more efficiently than high clouds. So they cool the earth because the reflected radiation they would also emit at high temperature. I'll leave all the numbers out of the discussion. This also I covered pretty much. Yeah, this I already covered in the morning. Yeah, somebody asked me about transient and non-transient. This is an example. See, if you double CO2 and wait for a long time, then you get these so-called liquid releases from 2 to 4 degrees. But in a climate model, which involves Indian Ocean, if you want to wait till it hits a steady state, you have to wait for at least 500 to 600 years at least. So they're so expensive to run models. So there's another one which is called transient response. You allow the CO2 1% per year and stop when it is 2 CO2. Don't wait for it to reach a steady state, but it will give you much lower value than this. Okay. But the same information is there. The range is same, but the numbers are lower because we didn't wait for the ocean to reach complete equilibrium, which takes a long time and there's a lot of expenditure on computational time. But the general pattern looks similar. So generally people can use this because it's easier to get results here than wait for long. But these two are numbers are different, but the trends are same. Yeah, so this illustrates clearly that those models in which there was more cooling by clouds and a lower temperature change than those that is 1.2 degree, while those in which cooling by clouds was reduced due to either decrease in local attraction or increase, they were much higher sensitivity. So this is the point which is clear. We know what caused difference, but we're not able to reduce the range of values that are coming. Okay, so that was the discussion on feedbacks. And the main purpose of this discussion was to point out that climate models give a range of temperature response and for the same conditions that all models given. And that's primarily because clouds in the different models behave differently. And today we do not have a single way to tell which model is right. If you have good data for the past 50 years, 100 years about where the clouds vary in the real world, then we could have said this model is not right, that model is not right. But today we don't have that capability. So we have to look at the whole range. And as I pointed out, although the range is quite large, anywhere to 1.5 to 4, more recent work has shown that some of the models showing a very small temperature change have some defects, some problems. So if you look critically at each model and find out its weak points, then the general consensus on future modeling is that 1.5 is not something which really happens. But those models have other problems. So everybody agrees that somewhere around 3 degrees is what looks reasonable for those models which get most of the present day. Because I want everybody to remember that when a climate model is built and is run, you have to ensure that certain things are right before you run the model for future climate. So the following things are make sure it's correct. Otherwise, first thing they ensure that the model in the present climate gets albedo around 0.3. Model cannot get 0.3, you don't visit further. You go back and spend more time in adjusting model. Remember there are 50 parameters model. So you have a lot of time to play around with. We keep adjusting parameters until you get around 0.3. Then overall has to be around 239 to 40, otherwise only non clouds. So both these are adjusted. So that way things are better now than 20, 30 years back. 20, 30 years back, these numbers are not known because there are no satellites available. So now these numbers are very well measured, very accurately measured. That is a constraint of the model. Model must have an albedo of 0.3, must have an over 239. If that is correct, you have got some parts of the model right. Okay. Then of course, when these two are there, you must have this value around to 88, of course. These three should come together. There's one more constraint. And the other constraint, if you look carefully, is total water vapor. I create another now. Total water vapor also is constrained because today we have put back on water vapor that we had. So these four must come within the range of measurement. These are the ones which are measured reasonably accurately. We have an estimate rainfall, but rainfall is not that accurate, but I think few measures. Rainfall we have a 5 year now because of good satellite data. So these are the 5 values which should value for the present climate. That is 26. So you do all your adjustment of that, and then you run the model for future climatic things used. So what I want to do is that all the models presently here are models to satisfy these 5 constraints. Still, they have a range of value, of course. So these are not very bad models; these are pretty good models because they have been asked to correctly reproduce climate of 20th century. If you do that on a global mean basis, no, I can tell you very, very interesting cases. There are models which do very well global mean, but monsoon will not be there. That happens, but you don't worry about it because you want only global mean is right. So this is the situation. If you ask for correct spatial pattern, you're gone. That is a very tough task to ask. So generally, modelers are happy if they get global mean. Also, some are also realistic mean. Because you know the two hemispheres are not similar. The northern hemisphere has more land, there is more ocean. So the two hemispheres show interesting differences in the present climate, and that you should reproduce back. So there are 50 parameters. Ideally, I would have like have 50 constraints on the model. We want 50, but about reasonably about 5-6 constraints are there which ensure that the model is not too far away from real world. Then you do the doubling. Then you get these later values. So that's the state of the subject today. That in spite of all the constraints being imposed on mostly satellite data and other global data, so all the models are not too bad. They do correctly reproduce global mean rainfall, global mean water vapor, global mean temperature, global mean OLA, all that is correct. But when you run them to 100 years, you go in different directions. So that's the situation we are in. I don't think it's going to change dramatically in the next 5 to 10 years. So the advice I've given IPCC under this condition is that this is the present state of understanding of climate system. We have to make this with this uncertainty. And of course, all these politicians and policymakers don't like it. They say, no, give us more reliable data. But I can tell you that the same people who are very much upset that we are not able to bring precise prediction, they say this is not economic matters, much less science, much uncertainty. Most countries, including India and Africa, make decisions about bank rate, about this, about that, based on much less first principle calculation, much less understanding. But somehow here they demand that we need more. My argument is that in spite of all the uncertainty that climate models, we can be quite sure that the most probable increase is around 8 degrees. And that is quite serious enough for us to be active. We don't have to wait for better models and more accurate data. That is nice to have it. But I don't think that should be an excuse for not doing this. So that is the message from the models have improved a lot in the last 20 years, but still there is a range of 1.5 of 2 to 4 degrees, a factor of 2. But to me, I saw the distribution, which is skewed in one direction. To me, the chances of global warming, increase CO2, being below 2 degrees is very good. Very, very small. The way we are going today, it will be about 2 degrees and more like 4 degrees or 5 degrees. And that is serious enough for us to take action. Don't have to worry about more accurate models. So that will be, of course, part of research for many years to come. But we don't have to wait for it. But the attitude of many politicians and this, because that's way, maybe we get better results, then we can take, that's not true. Because CO2 has such a long lifetime, you cannot afford to wait much longer. The longer you wait, more difficult the problem is going to be, because you have to take more drastic action in the future. And sometimes what happens is that there is some complacency among people because the ozone hole problem which I discussed in the morning was solved fairly effectively. It's amazingly, it's the first major environmental agreement among countries in the world. For the first time, we voluntarily agreed not to release CFCs because of evidence from models and observation. First time. And that was achieved amazingly by leadership from America, by a president who was not known to be anti-environmental. So this is how that will take place. So somehow we took a decision, and once America took the lead, others followed. So because of that, we feel that this problem also, so it's not that simple, unfortunately. Because eliminating CFC was very simple. Because it was only air-conditioners and a few other things. The industries which use those chemicals were a very small part of the economic system. But unfortunately, carbon dioxide is a part of everything we do. There is no part of our lifestyle which is free of carbon dioxide. So, reducing carbon dioxide is a much more difficult problem than reducing chlorofluorocarbon. And that's why all projects are postponing this for another day, because one has to make a lot of unpleasant for this generation, of course. See, so the decision we have to take very hard, not democracy easy. We are asking the present generation of people to make some sacrifice so that they have to pay more for their energy cost, so that somebody in the future, 50 years from now, will not get money. So this is the new thinking. I don't think anybody in any system has sacrificed for somebody 50 years from now. Very hard problem to look at. So I understand politicians not being happy to look at the problem. And so I don't think it's going to be solved easily. But since I'm an engineer, I'm an optimist, and I think the only way this problem is solved in an easy way, without political interference, political legislation, will be technology. Now, this only a visual thinking cannot happen. What I've seen in the last 5 years is solar technology. It gives me a hope that something unusual will happen. And the price of solar technology is already come down dramatically in the last 10 years. Will go down even more dramatically. And there will be some miracle discovery on storage which is required. If those two happen, then people will voluntarily give up coal and oil. Nobody really likes it, but because we got addicted to it for the last 100 years. So if a revolution occurs in solar technology, which looks possible, then the transition from coal and oil to solar may take around 30 years. If that happens, many of these breaks are optimal. But we don't know. So my view is very simple, that this change will take place only if there is pressure from the public. In a democracy, forget about other countries. In a democracy, the pressure from the public on the policy makers will change. They don't do it voluntarily. No change in this world. And my only optimistic view is what happened in Germany. Germany is a very big society. I don't think Indian country is in that category. There is a Green Party in Germany. It was like Aam Aadmi Party of today's India, but very different because they focused on environment, not on corruption. Corruption was not an issue in Germany. So for the last 50 years, Green Party consisting of absolutely committed young people, that's